into our reactions, right? So we moved into chapter 6 and the stuff we move forward with after that. So what we'll do is we'll predict some products, and then we'll do some predict the reagents, and then we'll do some synthesis. So if there's any areas you'd like me to ask questions about, just pop that up in the chat and I'll make a question around it. Okay. All right, so let's look. Okay, let's take a little time on these three. Okay, let's look at the first one. This first one is the radical reaction, right? So whenever I go through these and I give these little things, these are the things that I think will help you remember, right? So remember, that's a radical. Radicals react with alkyl halides, right? And we can get the bromination. The second one, we have the alkene, right? This is the hydroboration oxidation conditions. When you think about that, that should give you you should start thinking about regioselectivity and stereoselectivity. And we know here its stereoselectivity is to the least substituted anti-Markovnikov. So we get the terminal alcohol because it's terminal and I have 2 hydrogens, right? I have no stereochemistry to worry about. The last one, this comes into chapter 13, right? This is going to be first step. We're going to pull the proton, and sometimes you can do this, right? You can look at mechanisms. So if we get that mechanism there, right, then what happens? That results in this. And so then we've got our CH3I, right, so our methyl iodide, and then this can react here to kick that off. Okay. All right, questions about this one? All right. Okay, let's look at a few more predict the products. Let's take a little time to work on this one. Again, I'm going faster than you would have on the test. Okay, you can have a little over two minutes per question on the test. Okay. All right, so let's take a look. So if we look at our Grignard here, right, we know that the Grignard is going to be pulling the electron density going towards the carbon. So therefore we know this is partially negative, partially positive. Right, so from that, this is going to be electrophilic. So nucleophile attacks electrophile, leaving group leaves. That would first give me the alcohol. Right, it would give me this first. But then the second step gives me a proton, right? So I could get the alcohol. Next one, we're doing a, that should be aluminum. A lithium aluminum hydride reduction. So a lithium aluminum hydride reduction with a carboxylic acid or an ester, both will give me a primary alcohol. Okay, so we get a primary alcohol there. This one we're going to get a dibromide, right? So we're adding the bromines, but here's one where stereochemistry is going to be important, right? Because the intermediate is going to be this cyclic, bromine, which means the second bromine has to come from the bottom. So this is an anti-addition. Okay. Questions about these three? Okay, so let's predict some reagents. Let's try these three. Okay, so here, if we look at this one, right? So we are going to get a Markovnikov alcohol, right? All right, so we're starting with an alkene. So I have two choices here. I have water and acid, right? Or I could use mercury acetate with water, right? If you don't use water there, then you won't get the alcohol, followed by second step, right? Sodium borohydride. Okay. In this case, is there any chance of rearrangement? Not really. I mean, we have a secondary position here, right? So if we end up the carbocation here, that's also secondary. So there's no driving force. There's no ring opening over here like we saw with that four-membered ring that opened on one of the test questions. So really here, there's no big reason not to use just water and sulfuric acid, right? No reason to use mercury unless you're going to get a rearrangement. And the next one, we see that we get an aldehyde, which if we look 1, 2, 3, 4, right? 1, 2, 3, 4. That means that we're getting a anti-Markovnikov type addition of the oxygen, right? That then turns into the aldehyde, right? Because we're going to the terminal position versus the internal position. And so therefore here we want to use one of our borane species, so either diisoborane or 9-ppn. Yes, H3O plus would work. Water and sulfuric acid is just the reagents you would add. Sorry, question in the chat. And then second step here, we would want to use, you know, our hydrogen peroxide and base. Okay. So that'll form the primary enol, right? Alcohol on the 1, double bond between the 1 and the 2, and then that'll tautomerize to the aldehyde. On this one, we see that we're adding the ethoxide group. So the question is, do we want to add this as the nucleophile, or do we want to add this as do we want to add it as a base promoted, or do we want to add it as the acid promoted? So if we had base promoted, that's going to favor the least substituted side, right? And this is going to favor the more substituted side. This has to do with hindrance, right? This has to do with stability. So in this case, where did we add the ethoxide? Well, we added it to the primary position, right? So we added to the primary position. So that means we're going to want to use the base promoted. And then, you know, as far as reagents go, I want to put a counter ion there. So something like this, and that will give me my product, right? So we have two different possibilities there. Okay. Questions about that? Okay, let's try a few more of the reagent ones. Okay, let's try these three. Okay, so let's take a look. In this first one, okay, what we need to be thinking about here is we're forming an elimination, right? So this is elimination. And if we look at this, we are going, you know, if we think about our beta hydrogens, we have beta hydrogens here and beta hydrogens here. And we're substituting to the more substituted side, right? We're eliminating the more substituted. So this is going to be Zaitsev, right? And if we have a secondary like this, Zaitsev's, potentially I could do this through an E1. So all I'd have to do is have concentrated sulfuric acid, right? Or, right, or I could use turn this into the tosyl chloride, right, with pyridine, and then follow that with just a normal small base, right? But in this case, secondary sulfuric acid, you could get this one to work through an E1 process. This would be E1, this would be an E2. The next one, we see that we start with the same starting material, but now we're eliminating to the least substituted position. This is the Hoffman elimination product. To get the Hoffman elimination product, I have to do E2, right? So I'm going to have to turn that into a good leaving group. So I'll use my tosyl chloride. But then in the second step, I want to use my big bulky base, right? So something like T-butoxide, that's the standard one. This is an E2, but because it's bulky, it's going to give me the Hoffman elimination product. Okay. Questions about those two? And the last one here, this is not the way it's usually shown, right? But I could show, I can do it this way, right? Which is just adding in the anion. So just switching it up a little bit so it doesn't throw you off if you ever see it. Okay, questions about these? Okay, let's do a few synthesis questions now. Okay, let's try those two. It'll be a little bit more time this time. Okay, let's take a look. All right, first, you need to kind of evaluate what's going on. Remember retrosynthesis cerumen, this is my starting material. You know, this might be something you want to mark down on your notes. Again, bring some scratch paper, bring some scratch paper so you can play with these. It's hard to do these just staring at a screen. So bring some scratch paper to work through them. Okay, so if we look here, we have 3 carbons, right? Here I have 5 carbons. So I know I'm going to be adding 2 carbons, right? If we look at those 3 carbons and then we know we're doing a change, where those 3 carbons, they could actually be almost anywhere But if I look at 1, 2, 3 and think 1, 2, 3, that means I'm adding these 2 carbons, right? 1 and 2 to get the 5. Now, with the bromide here, I don't have the hint is that I'm making carbon-carbon bonds. And with the bromide here, I don't have a triple bond, right? So I have 2 ways to do this. So the final exam is going to be open at 8 a.m. on Monday. So that's our official time period. So it'll be open from 8 to 10. Extended a little bit for those that have accommodations. Okay, so starting material, right? So we have a bromide. Since we have a bromide, the hint is that we're probably going to be going through a Grignard, right? So we have 2 good ways to make carbon-carbon bonds. At this point, one of them is Grignard, the other one is the acetylide. So if we go to the Grignard, then the question is if this is where I'm dividing it, right? How do I get the position there? And the way I do that, and I keep changing colors on y'all, sorry. The way I do that is by using the epoxide. Remember, the epoxide is a way to add 2 carbons with a terminal functionality. So then when I add the Grignard, it's going to give me this, right? So 1, 2, try to add a proton source. And then all I need to do is oxidize that up. I want to use a mild oxidant, right? So PCC and methylene chloride. Okay. All right, questions about this retrosynthesis? Okay, this is an important strategy, the way to add 2 carbons, right? Adding 2 carbons with the terminal functionality. The next one, we see very similar thing, right? We got 5 carbons here, we got 3 carbons here. Because we've got the bromide and not the acetylide, right? We're probably going to be going to this. Oh, I forgot to add the reagents. Magnesium and ether, right? So magnesium and ether. That's just a shorthand for ether. Okay, so we get here. Now when we think about it, if this is 1, 2, and 3, 1, 2, and 3, then now what I want is I want the functionality exactly where it's adding. So thinking about where the functionality adds, we're going to get this, right, by adding just the aldehyde. Let me redraw that. By getting the aldehyde into the water, okay? Questions about that one? Okay, all right. Let's try a couple more. And again, if you have any requests, just put it in the chat box. This one's a little longer. It's going to use a lot of your reactions, so we'll give you a good amount of time on this one. We'll just post one. Okay, let's take a look. Okay, this one looks more complicated than it is. If we again start at the beginning, our carbon skeleton, we have 4 carbons here. Right, we have 4 carbons here. Okay. Note that we have stereochemistry here. Right, so we're going to have to be specific on our stereochemistry. Over here, we just have an alkane, right? So with an alkane, we don't have a lot of functional groups, but we're going to end up with a species that has two functional groups, right? The diol. So we need to think about ways that we can increase that and have functionality at 2 positions. Okay, one of the ways to do that is to make sure that we can get to 2 functionalities, which means we need an alkene, right? If we also think about how we would form a diol, right? The diol needs to go through an alkene, okay? But how do we form an alkene? Well, we need something to eliminate to form an alkene. So I'm going to need to do some type of bromide. So if we look at our process here, we're going to need to add an activated group so that we can have something to work with. We're going to need to form the alkene, and then we can use the alkene to get to our final product. So let's start with this. We're going to react that with Br2 in light, right? That will selectively give me the secondary bromide over the primary bromide. Then I can do an elimination. Here, all I need is a good base. I could use DBN or DBA, but I'm going to do an E2 style elimination, but with a small base so that I get this formed, right? This will be the more stable, so I should form that one over the cis. And then from here, then I can get the osmium tetraoxide followed by, no, not the UMSO. Is it sodium NMO? NMO. Well, that's those 2 together. So if I erase that, that's correct. Okay. Sorry, I'm trying to recall the reagents. Okay, we could have also used potassium permanganate in base. Okay. Right, so we're going to use that to give this. Questions about this one? Okay. Okay, let's try this one. Okay, so for this one, okay, we can obviously see that this is 2 carbons. And here we have 1, 2, 3, 4, 5, 6 carbons. We can see that we're going from the alkyne to this halohydrin. And if we look at that change here, when we look at this, we can see that with our two functionalities right here in the middle, that we're probably going to be breaking right there. So our strategy here is probably going to be to build this up. And then if we look at our stereochemistry, we can see that halohydrons form anti, and that's what we're showing. So I want to go to trans, and then from the trans I can get, and it's nice that it's symmetrical, right, that I can get the product. Right, so my big points here to think about is that I want my alkyne right in the middle, right, it's symmetric. And then right here, this is a big one too. This is one where students usually will make a mistake. I don't want cis, I want trans, because my base structure, right, is trans, and the bromide in the alcohol, I'm getting what I should get, right, which is anti-addition of the halohydrin. Okay, so if we put in our reagents, here we're going to use, sodium amide, right, followed by our ethyl bromide or ethyl iodide. Then we'll do that again, sodium amide, followed by our ethyl bromide. Then to get the trans, I need a resolving metal reduction, right? So that's sodium in ammonia. Okay, and then to get the bromine, the halohydrin, I just need bromine and water. Okay. Yes, sodium in ammonia for the alkyne to the alkene, not the alkane. To go from an alkene to an alkane, you just use hydrogen and palladium, and that will go to that, right? So this is okay. All right. Okay, questions? Any other reactions you'd like to see how we use? We're running low, so only got one or two more. So we've done some reactions. We've done some alkynes, done some alkenes, some alkyl halides, alcohols. Okay, let's do. Yeah, we'll do some cyclohexanes. Yeah. Let's try this one, and I'll do a cyclohex. This one's not too long, and then we'll do a cyclohexane. Okay, this one's pretty straightforward. The trick on this one, right, is we're using two of those bromides. But if we add sodium and sodium thioate, right, so that's going to give us this. And then if we take two of those, right, and we don't have to say two, but it would be nice if we took two, and we take bromine, sodium hydroxide with hydrogen peroxide. Oh, and so water, not hydrogen. The bromine is our oxidant. Right, that's going to give us the disulfide. Okay. Oops. Made it too short. Okay, this one's a little tougher, so we'll take a little bit more time. Okay, let's take a look at this one. A little bit more complicated, but the thing to pick up on is, as you can tell from my mistake, right? This is 6 carbons and this is 6 carbons. But because I've changed from a cyclic to an acyclic, I know that somewhere in here, right, I'm going to be cleaving a carbon-carbon bond. And if we're going to have to cleave a carbon-carbon bond, then we need to think about how we could cleave that, right? And we know that we could do ozonolysis. Right, to get this, right? So that looks like what we need to do, which means we're going to have to take a couple of steps to get to an alkene. And then we're also going to have to take a couple of steps to get from this, dialdehyde to our diether. Okay. So if we start right with our alkene, we're going to add bromine and our light, right? That's how we react with alkanes to get them to the bromine. Then we can do, any good base. I'll use I should have used the methyls, but just so you'll understand, any good base here will give me elimination. Then ozonolysis, I do the ozone, right, followed by the DMS, right, which would result in DMSO. We saw that in chapter 13. This gets me to the aldehyde. Okay, so we get the dialdehyde there. And then here we just use an excess of the sodium borohydride. That will get me to the alcohol. And then here we could do it in 1 step or 2 steps. 1 step, you just kind of keep going, but I'll do it in 2 steps because it works a little better in 2 steps. So we use the sodium hydride, right? And then we add our methyl iodide. And then we do that again. Okay. Let's do one more quick one with an alkene, with a cyclo-X alkane. So Okay, so we have a little bit of time. Let's go ahead and take a look at this one. All right, and this one, we have 6 carbons. Right, and over here we have 9 carbons. And it's pretty obvious that we're adding those 3 carbons. Now we could add those 3 carbons as acetylide, but most likely this is going to be added as a Grignard. And then if we think about it, we have an alcohol at the 1 and the 2, which gives me a hint of what's going to be happening here. What's going to be happening is I'm going to take this to the epoxide, right? And then I'm going to add my Grignard. So we take our alkene, react that with, MCPBA or any peroxy acid. That's going to give us our epoxide. And then our epoxide, we react that with our Grignard. So we want this Grignard, right, followed by water. And that earlier question about how many synthesis we're going to have, this is a complicated one, but notice that it's really only 2 main steps. Yeah. All right. And again, this idea of this epoxide is going to be something that you want to look at. Okay. All right. So we're